these guys in person. So without further ado, Markus, thank you very much for taking the time. We're really looking forward to your talk, and off we go.
Thanks. Check. Great. Thanks, everyone, for coming out. My name is Markus. I'm the lead developer on OpenDeep, an open source platform for deep learning in Python. And today, just do a few tutorials for you guys to get your feet wet in deep learning, actually how it works. We'll do a little bit of math. I know it's a little scary sometimes. And then I'll show you how to do some more complex models using the OpenDeep package. So first of all, what is deep learning? So I really don't like to make this analogy, but it's easy to understand. It's loosely based on the brain. So you have different layers that form a hierarchical representation of whatever input you have. And what does this give us? This gives us something that forms a useful representation. Now, what is useful? Well, data can be complex, whether it's images or speech or just random databases that you may have. So a useful representation is one that can actually detangle the factors of variation on your input space, something that's highly complex and make it a lot less complex. An example of this is something that can learn a face from its base components, say the edges that form the contours of a nose or an eye, piecing those bits together in a hierarchical manner. And what does this do? This automates feature engineering. So with a lot of classical machine learning techniques, you have to first figure out what base features of your data are important for your end goal. With deep learning, what you can do with throwing lots of data at it is have the algorithm itself figure out what is the most important parts of your input data, and then use that representation to perform your classification. And this works just because it composes nonlinear transformations of your data. And I'll go into a little bit more about why that works later. But essentially, it's Legos. You have these base layers that can stack onto each other to form a much more powerful representation of your input data. Now, a basic example of that image detection I was saying with faces is it shows different layers of a neural network can learn. The bottom layer learns these edge detectors, which combine to form noses and eyes, which combine to form the faces. Similarly, with audio data, you can have your chunks of waveforms, which form the actual utterance, which can then be classified. Similarly, again, this is with images. Using colors, it learns filters that actually extract out textures of objects, and uses those textures of objects to classify what's in the image. Now, a little bit of basics for linear algebra refresher, because that's how all of this works. So for linear regression, you're basically trying to fit a line to your data points. If you have a single dimension, x, you're trying to find this parameter of the slope that allows you to minimize the distance between your output and what the actual y value was of your data. And it also has a bias, that's the intercept. And if you have multiple data points, instead of just a single dimension, you can think of this as a parallel by having a weight for each of those input dimensions to then form your output connection. And when you have a lot of input dimensions and a lot of weights, you can stack them together as matrices. It didn't turn out so well, but as you can see, you basically just have a matrix multiplication that's your linear transform of your input data plus some bias, and you get your output. Now, to make it nonlinear, all you have to do is take a nonlinear function and put it on top of that matrix multiplication. So now you're just transforming your input data, your x's, with your weights y, and you're squashing it with, say, a sigmoid logistic function. There's your matrix multiplication, and your sigmoid logistic function is just 1 over 1 plus e to the matrix multiplication. And now it's between 0 and 1, so that gives you a probability. So that's all you need to know to make pretty much any neural network. So what a neural network does is it stacks these nonlinear functions on top of each other. Now, the reason you need it to be nonlinear is that if you compose multiple linear transformations to each other, they all reduce back down to a single linear transformation. So you don't get any increased power of representation by stacking linear transformations. So by gating it with this nonlinear activation, you get a lot more representational power by stacking more layers. And essentially, an MLP is a multilayer perceptron, which is your basic feed-forward neural network. Essentially what it's doing is its output is a bunch of multiple logistic regressions. You're getting a bunch of probabilities as the output of what each class is in your final vector of outputs. Now we're going to do a little toy problem. We're going to program an MLP to classify an image into its digit. So the MNIST is a popular academic data set. It's basically a bunch of these handwritten digits, 0 through 9. It's 28 by 28 pixels, and you basically want to classify its output digit class in a vector of 10 numbers. So how are we going to build this? Well, first our input is 1 by 28 by 28 vectors, or it can be done in batches, so you can have an n number of batches by 28 by 28 vectors. The first hidden layer is just what we did before with that logistic regression. You have your matrix multiplication by some weights, you have your bias, and you transform it into this hidden layer. Now this hidden layer, you have a parameter you can play with, which is the number of hidden units you're using. In this case, we'll just use 500 hidden units. So that means we just need a matrix that's 28 by 28 by 500, and that'll transform our input space into our hidden space. And then we need our bias for that as well. Now to get the final prediction as the output, all we do is take that hidden, multiply it by some more weights, and squash it with a softmax function. Now the softmax function is basically a generalized logistic regression, so you get probabilities. And that's the whole point. You want probabilities of each class as your output. So in this case, we just need one more additional weight matrix, 500 by 10, to transform our hiddens to our outputs, and then a bias vector. And that's all you need to do for an MLP. I'll show you real quick. In Theano, that's really easy to do. So first, as with any project, you like to look at the data a little bit. So here we're going to load the MNIST data source. This comes from Montreal's website. You can see where to load it. Basically, we're just going to print out an example of what the input looks like, and then one of the labels looks like. So here are the shapes of our data. We have 50,000 training images. We have 10,000 validation images, 10,000 test images. The input is a 784 sized matrix, or a vector. And then an example label is just the digit 5. We can show this as a number. We get a little image output there. Those are the first 25 MNIST images. Now in Theano, Theano is a great symbolic math package for Python. What it does is it lets you write programs as you would write equations. So writing these matrix multiplications, getting the output, and compiling that as a function is really easy to do. And one of the magic things about Theano is that it does automatic differentiation for you, so you don't have to ever calculate derivatives by hand. If you change up the network architecture, you change out the activation function, you don't have to go in and then specify gradients and such when you're actually training the algorithm. So you can just write your equations, you have some optimizer that's separate from your model, and it'll be able to train based if you change your model up. So to actually create these equations in Theano, you have to work with basically symbolic variables, right? So we're going to create our symbolic variable for our input x. If you remember, it's just the image. So we're going to make a matrix where the number of rows is the number of image examples we're going to compute in parallel, and the columns is just the 784 input data that our image has. So we just create, another thing with Theano is that it works on the GPU, which makes things a lot faster because everything is matrix multiplications. The GPU is optimized for that. And it works seamlessly between CPU and GPU. So we're just going to make a matrix to represent our input. Now, to compute our first hidden layer, all we needed was our weights matrix and our bias vector. So here, we're going to use NumPy to create a random initialization of this weights matrix. So whenever you initialize any parameter for these models, it's very useful to use a random initialization so that you don't get stuck later on if you just start with all zeros or all ones. It helps the training process. So in this instance, we're just going to use a normal Gaussian distribution for sampling our weights to create these matrices. Another way you can do it is by sampling from a uniform distribution that's used a lot. There's a lot of literature on initialization to actually make it work well. So we're just going to make a random matrix of 28 times 28, which is 784 by 500. And then we're just going to make a 0 bias vector of 500. And then for Theano, to make these into symbolic variables you can then use later and update as the function is training, you have to make them into shared variables. And shared variables are a way to take an actual number and put it into the symbolic form that Theano can work with. So we created our symbolic input, and now we're going to create a symbolic weights matrix and a symbolic bias vector. And then to create our hiddens, all we have to do is do our tanh activation function of that dot product matrix multiplication between the input and the weights plus the bias. And that's all you have to do to calculate our first hidden layer. Write it exactly as you would for a math equation. Now we can pretty much do the same exact thing to get our outputs from our hidden layer. We need to create one more weights matrix to transform our hiddens to our outputs, one more bias vector for our outputs size, and then we can just write the equation literally for our y output label of the softmax, which is the way to get the probabilities of the vectors, that's our nonlinear function, of that dot product between the hiddens, the weights, and then you add the bias. And then, of course, we care about the actual predicted label, right? So we're getting a vector of 10 possible labels, each with the probability that that label is the correct one. We want the argmax, which is picking the index of that vector probabilities of the label, and that gives us the actual number. So if the first element is 0.9 and all the others are lower, it'll pick the first element as the correct label, which would be the 0 digit. So we just create those as we would the equations writing them. Yeah. So that's all you need to do to actually instantiate the network. Now, for training something like this, you can train it all at once. And what you need to do is have a cost function, as you know from other machine learning courses. And for the MLP, because we output probabilities, what we like to use is the log likelihood. And what that is that's the probability that our model gave out the actual correct label given the target that we want. And because the MLP actually outputs probabilities, all this corresponds to is picking out the probability that we thought was the correct label and using that as the likelihood. Then we take the log of it and the negative mean, and that'll give you your negative mean log likelihood, which is the cost function we're going to minimize when we're training. And all that is a score of how well our model is actually doing based on our input. So we have our outputs, and we know what's correct. We have our model. We know what probability it thought the correct output was. We want to increase that probability, and we want to decrease all the other probabilities. So to actually train it, we use something called stochastic gradient descent very often, and its variance. In this case, what it does is it takes a single input example, or batches of them in parallel, and it will calculate the gradients of the weights with respect to that cost. So our model parameters are the weights that we defined. That's what we're going to wiggle around to try to decrease our cost function. So that's the weights from the hidden, the input to hidden to output, and the two bias vectors. So what happens is we have to calculate the gradient of that cost function with respect to those weights. And the gradient will actually show us what direction, positive or negative, we need to step each of those values to actually reduce that cost function. It'll just wiggle the weights a little bit in the correct direction to reduce the cost overall, which is to increase our probability that we're correct. So here again, for our cost function, we need to represent the correct labels, again, as a symbolic vector. And in this case, we're getting a vector of digits, 0 through 9. So we'll make an integer vector as a symbolic vector. And then the cost function is simply the log likelihood as before. So the log likelihood is our output, the log of our output, which is the probability. And then we pick out what the correct label was, so the probability of that correct label. And our cost is just the negative mean of it. And again, the parameters, everything that we need to learn about the model is right here. It's the two weight matrices and the two bias vectors. And Theano's great because you can just do the Theano.grad function with the cost with respect to parameters, and it'll automatically figure out, given an input, what direction to move those parameters, and it'll actually let you update them. Now with stochastic gradient descent, we do something called a learning rate, which lets you take a small step in the correct direction, because you don't want to take large steps with every example, because then a single example will change your model parameters too much each time you run through it. So we're just going to create our updates. We're going to create pairs of what the parameter is and what we need to do to change that parameter, the wiggle direction. So we're taking our parameter, we're pairing it with the parameter minus the small learning rate times the gradient, which is the step it needs to go. So that's all we're doing here. We're taking the gradients and we're updating the parameters in the correct direction to actually decrease our cost function over time. So that computed our costs. And now all we need to do is compile our functions. So Theano, right, we created the symbolic computation graph, basically, of transferring our input to our log probability as output to the cost function. So in our training function, we need to input the two symbolic inputs that we had. One is our original inputs x, which is the original data, and the other input we need to calculate the costs is the correct labels, which is that symbolic vector we made of labels. The output, just so we can see how things are going, we're going to just output the cost so we can see it decrease over time. And then the updates, this is where Theano gets a little tricky for some people, is you have to include all the updates when you're running a function. It will actually change those shared parameters based on the updates that we described before for gradient descent here. So you have to pass those in so it knows to change it every time. And then downcasters, you can ignore that. And same thing for test. Because we're not calculating the cost, we only care about the input. We're just going to output our y-hat, our argmax, what we thought the actual label was. And that way we can run it on our test data and compare our outputs to the actual test results and get an accuracy rating. And one thing about Theano, oh, that compiled quickly. One thing about Theano some people don't like as much is that when you're creating these symbolic graph representations, sometimes it takes a long time to compile, calculating gradients especially, because it actually optimizes your equations for you to try to make the runtime a lot faster. And finally, for actual stochastic gradient descent, we're basically going to do mini batch training, which takes batches of, say, 100 of those images at the same time, computes the gradients across all of them, and updates the parameters as such. So we can do things in parallel. So here, we're just taking our train X, which was the training image data set, the entire 50,000 by 784 matrix. We're going to extract out a batch of it, and the batch size we can play around with to make it larger or smaller to parallel process. So here we're going to go through batches of 100, calculate the costs, get the accuracy from our test results, and then print out what the average across all batches was to get the entire data set. And then we're just going to do the same thing with our validation and test sets that we had before, go through batches of them, and print out the accuracy of our predicted y-hat labels with the correct labels from the data set. And here it should start running. There we go. And you can see it's just running. So every time it goes a row down, it has run through the entire data set a full time in chunks of 100 at a time. You can see our cost function is decreasing, our accuracies are increasing, and it's working pretty well. And all that was creating two symbolic variables, one for our inputs, one for our labels, creating 4 model parameters, our 2 weights matrices, 2 bias vectors, and then creating the cost function, how to relate our output with the labels, and our gradient updates to make it go. And it should just go for 30 epochs. You can have it keep running, and it'll get a lot better. But to save time, there's that. So that's how your basic feed-forward neural network works. And if you want to add more layers, you can do the same thing you did from your input to hidden. Just keep on stacking them. Just create more weights matrices, create more bias vectors, keep multiplying the outputs from the previous layer, and you can link them all together. And the same exact code for training and everything should still work. One final thing is that in machine learning, something called regularization is used a lot to make sure you're not overfitting to your training data. And what's used in neural networks is something called dropout, which does a masking noise over all of your units in every layer, sets some of them to 0, so that your individual neuron units can't memorize some aspects about the data. And your network overall just can't memorize your input distribution. And so this lets you generalize better to real-world data. But our next model, the denoising autoencoder, is going to use noise, so I'll show that. This is the part where we get away from labels. Most of the world has data that's unlabeled. You can scrape the internet. You don't necessarily know what topic people are talking about on forums. If you're scraping that, there's a lot of unsupervised problems. So how can we deal with all this data that is unsupervised? Well, we can actually turn it into a supervised problem And what we want to do is actually create a model that has our input data, and we want to transform it to this hidden space, doing that nonlinear activation over the transform, and then reconstruct what the original data should have been. And in this case, we're creating a hidden representation that learns a useful representation for reconstructing the original input given, say, a noisy input. So autoencoders, they're also a very simple model. All you do is you have your hidden layer defined in the same way that you would have an MLP hidden layer defined. Just a nonlinear function across the matrix multiplication. And now you need to decode that back into the input space. So you don't actually need a second weights matrix. You can do something called tying your weights, which is just taking the transpose. You're doing the opposite transformation you did for the hidden space, and you're putting that to go back into the input space. And then you're doing the nonlinear activation on top of that. And that is an autoencoder. And then for cost, because you don't have probabilities anymore, it's not a softmax function, it's some other nonlinear function. You do the reconstruction error, which is normally your mean squared error, which is very common in other machine learning tasks. Denoising autoencoders do the same exact process, except before they create that hidden layer, they add noise to the input, just to simulate that you're having real-world messy data. And this model is actually very useful for things like reconstructing missing values in a database, or if you have very messy input data that's just missing some features. As long as it's not like categorically missed across all your data, you can use an autoencoder to reconstruct what that missing feature should be. So the denoising aspect takes your original input, corrupts it with some noise function. In our case, we're going to use salt and pepper noise, which randomly sets some bits to 0 or 1. Then does the autoencoding process on that noisy input. So you create the hidden layer, and then you reconstruct what the original input should be from that noisy bit. Now, I'm not going to go too much into the probabilistic view, but it's pretty cool. What this does is it actually lets the hidden layer learn the probability of generating your input distribution over time. Because this process goes back into your input space, you can just repeat it for as long as you want. So you can take your original input, you encode it to the hidden space, you decode it back into your input space. That's different than the original input because you're not going to be perfect. You can then take that, corrupt it, encode it, decode it, take that, corrupt it, encode it, decode it, and you can continue this and have your model start generating your entire data distribution. And there's been a theorem in some papers that show that if you do this forever, you get the stationary distribution, which is known as basically you can generate all points of data in your original data distribution. You're learning the probabilities that your data has based on the hidden values. So to actually program one of these denoising autoencoders, it's very easy. It's the same process as before. It's actually easier. We have one less weights matrix we need to make, but we do need to add some noise. So first, we're going to take the same input vector. We're going to make that symbolic again. Then we're going to write a noise function to corrupt it with salt and pepper noise. Then we're going to calculate our hidden layer. This time, instead of 500 units, which was less than the 784 inputs, we're going to actually make it bigger, 1,000. This is called overcomplete. And this is useful, especially for denoising autoencoders, because we're already creating the input, a corrupted version of the input. So we don't have to worry as much about memorizing or having all the neurons learn all the information. Before, because we didn't have noise, we would want a smaller hidden layer size than our input size, so it can't just memorize the exact input. And then we're just going to create the reconstruction by taking the transpose of our weights of the hidden layer and applying the activation function. And here's an example output, actually, of what it does. So you have your input on the left, it adds the noise on your middle input, and then it creates a reconstruction of what it thought it was. So again, I'm just putting all the imports up top this time to clean it up. We're going to look at our data. Again, we're the 50,000 by 784. And here I'm also going to instantiate everything in the same place so you can see it better. These are all the hyperparameters we can play with. You have our input size, our hidden size, and because we're sampling our weights initially from a normal distribution, we're going to have the mean and standard deviation of those. And then we're going to have a noise level for the noise corruption that we're adding. Now, walkbacks is actually that repeating function I said before where you take your input and reconstruct it, then use that reconstruction to reconstruct a new one. That's called a walkback, where you can take a certain number of these and actually the cost function is going to be the sum of all the reconstruction errors between the generated inputs and the original one. So you're anchoring it. You're letting the algorithm walk around what it thinks the data should be, and you're telling it to kind of point back to what that original data point was. We have our learning rate like before, our batch size, number of epochs like before, and check frequency is just going to be, I'm going to spit out some images every this number of epochs. Okay, so if we're actually creating the computation at Theano again, we're just going to create our symbolic matrix X, our shared weights variable Wx, which is going to transform the input to the hidden space and the hidden to the input space. And then we just need our two bias vectors, one for our hidden layer and one for our input layer after the reconstruction. Now our noise function. In Theano, you can have noise in something called a switch. And this allows you to turn on your noise during training so that it doesn't memorize your training data, and turn off your noise during testing because you're assuming your test noise is messy to begin with. So what we're going to do is we're going to define a function that creates this switch variable from the input variable so that you can take the noise and arbitrarily turn it on or off during runtime. And again, whenever you make something that you want to change in Theano, you have to make it into a shared variable based on the input, just so that you can play around with it as the equation is actually running. So we create a shared variable called the noise switch that we're going to set to 1 or 0 if we want the noise to exist. And we're going to define this function, salt and pepper, that basically just takes a masking noise, takes some bits randomly, and it's going to randomly set those bits it picks out to 1 or 0. That's salt and pepper noise. Compile that. Okay. And then all we do for our function is, for each walkback that we have, we take the input, we corrupt it into a noisy version with the salt and pepper. We take that noisy input, we compute our hiddens the same way we did with an MLP, and then we construct our reconstruction just by taking the transpose of those weights with the hiddens, and pretty much the same exact format. You can see there's a pattern here. All of the basic building blocks for neural nets are really simple. It's just the matrix multiplication, a bias vector, and some nonlinear function. And then for our walkbacks, we're just going to append our reconstruction to the end of it so that we can use that reconstruction for the next input to this sequence of this walking graph. And then reconstructions, we're going to get rid of the original input we seeded it with, and we're just going to have our reconstructions be what we generated from the model. Cool. So our output, the final output of our model, we don't want to just give back all of the reconstructions we just gave. So we're just going to give the final walking reconstruction that the model gave. So we'll just do the last one in the list. And then the cost is going to be the sum of the reconstruction error of all of those walkbacks that we had against the original input, what it should be. In this case, because all the inputs are binary cross entropy is a good analog for what reconstruction error is. Again, our parameters is just the one weights matrix, the two bias vectors, and we calculate the gradients, and the parameter updates the same exact way as the MLP, where the gradient is telling you how to adjust your model parameters to make sure the cost function goes down. The same exact way as before, we're going to create these functions that we can then call on our data. The input, in this case, is just x because we don't have any labels. Our cost function and our updates are calculated as they were before. Same with the test function. We're just going to actually spit out from our test function our reconstructed input so that we can visualize it as an image. So it should compile those. And it's compiled. Okay, and now the stochastic gradient descent is exactly the same as it was before, except we don't have the accuracy numbers because that doesn't exist anymore. It's just a reconstruction. So we're going to append the train costs and spit out what the average cost was. And then over our check frequencies, what we're going to do is we're going to run that test function, which gives you back the reconstructed image. We're going to use a helper function to actually make that image into a readable, savable format, just so you can take that vector of 784, put it into the 28 by 28, and then save it as an actual image. So it'll save these checkpoint images. And then at the end, it'll also create an image of what filters our hidden layer actually learned. Now this is cool. We can actually visualize what parts of the image the neurons are actually corresponding to. So in the filters, you'll see like curves where you'd see like the 8 and other things that are kind of the activation map of what this hidden layer is learning. We can have that run a little bit. This one takes a little bit longer because we're doing the walkbacks. We're calculating all these reconstructions and getting the cost from that. So I'll let that run while I talk, and then you can see the weights afterwards. So that's all you need for that unsupervised model. And you can see like there's the trend, right? So it's very simple. You're just doing matrix multiplication, nonlinear activation, you're stacking them, and you're getting the output space, what you care about. Now, how do you make something really complex? The RNN-GSN is stuff that I've been researching for my master's thesis, and it's basically a way to combine two different networks that are good for two different things. So a recurrent neural network, as you might know, is good for time series data because it has some sort of internal memory that changes over time. And then the second model we're doing is a GSN, which is basically just a generalized version of that denoising autoencoder we just made. And what we want to do with this is we're doing a task of unsupervised sequence prediction and generation. So what we're going to do is we're going to take a sequence of these MNIST images, and we're going to try to create a hidden representation that learns what that sequence is so that we can just generate the sequence of our input data distribution whenever we want. So we're going to go into a little to each of the components, the RNN and GSN. The RNN, this is from Andrzej Karpathy's great talk he had here, basically has this internal state that gives you some output based on the current input as well as the previous hidden state. So the hidden state acts as your memory. You have a connection between each layer. So you can start with your initial hidden state, your initial input, calculate an output. Then you need to calculate your next hidden state from your next input and your previous hidden state, and you calculate an output. The output's not dependent, well, it can be sometimes, but your output's not dependent on any other previous outputs. It's the hidden states that get the memory of your entire network. The GSN, you can think of it as a denoising autoencoder with multiple layers. Instead of one hidden layer, it has multiple hidden layers that can all interact with each other. But you can think of each of these capital H's as a hidden layer from your denoising autoencoder. It just performs a more powerful representation of the input data. And now the architecture we're going to do. We're going to let the recurrent neural network learn the time series, and we're going to let the GSN learn the reconstruction complexity, basically. So what we're going to do is we're going to take the recurrent network, we're going to have its outputs be the hidden layers for the GSN. So you can imagine the output from the recurrent network calculating the hiddens for your denoising autoencoder, and then having that denoising autoencoder reconstruct what the original input should be based on those hiddens. So that way, the recurrent network only has to learn how to output to the complexity of the representation that the GSN is learning. And that complexity is a lot lower than the original input complexity, because an image is a fairly complex space. So that lets the RNN devote more of its resources for learning the temporal dependencies, and the GSN devotes its resources for learning the input to a hidden useful representation. So we're just going to chain these together. We're going to take an input, x, we're going to calculate a hidden recurrent state. We're going to take that hidden recurrent state, calculate the hidden GSN state, which will then predict what the next x should be, which is x hat. And then we're going to take the reconstruction error of that x hat with what the next input actually was and use that as the cost. And we can continue this for however long our sequence should be. And as you can see here, an input sequence, if you read from top left to bottom right, this is 0 through 9, 9 through 0 repeating. And it'll generate on the output sequences that look like this, which is kind of a generalized representation of what it thinks that sequence is, and it generates it fairly well. Our denoising autoencoder is pretty much done. We can look at some of its outputs first. So here is denoising autoencoder test output images. On the left is the original input. On the right is its denoised reconstructed output. And they look very similar. And it'll only start to look even more like the original input the more we train it. And this is with test images, so this is stuff it's never seen before. The filters. Oh, yeah. The test 0 looks like this. You can see it's still very noisy. It does learn pretty quickly, start where the data distribution is going. You can kind of see the outline in white, but it's still very noisy. And then at 50, which just popped up, it has learned that we don't care about all that other surrounding areas of the input, which is kind of remarkable given that, I mean, it's a 784 size vector. It's learning to reconstruct it pretty well. And it'll actually get it pretty much perfect if you run for like 500 epochs. The reconstruction error gets pretty low. And here's a quick example of some of the weights it's learning. These look really noisy because it was stopped early from training, but you can start to see these curves, these lines, these edges that it's learning of where the numbers actually take up space in your input space. And this is all 1,000 columns of our hidden representation. Cool. So the RNN-GSN, I'm going to use the OpenDeep package. A quick aside, the OpenDeep package is a way to make it easy to compose these layers so you don't have to write the matrix multiplications every time. You don't have to create the parameters every time. You have a configuration of all these things. So, for example, creating the multilayer perceptron in OpenDeep is as easy as making the model, which is a prototype that we can add layers on sequentially. We're going to make 2 hidden layers, which are your basic multiplication and nonlinear function layers. We do the input size, the output size. We can specify the activation function that we're using, 10H or sigmoid or ReLUs. We can add dropout noise. We can change how the weights are initialized. You can configure everything that you'd want to as a research package by creating these layers without having to actually program any of that. So we can add 2 hidden layers really quickly, add a softmax layer, which is that classification output, then output size of 10, and then run it with stochastic gradient descents because the optimization technique only depends on the gradients. It doesn't matter what the model was. So you can have that separate. You can have stochastic gradient descent. You can have its variants that don't really depend on a learning rate as much, like add a delta, add a grad. You can change up the optimizer to work a lot better than your vanilla SGD. And then it can run the same way. But basically, the package is meant to make it easy to compose very modular networks and configure them exactly as you would need. So I'm going to do an example of actually creating a new model instead of this prototype where you add layers. The new model itself is the RNN-GSN. We're going to do our imports up top. Aren't too important. Then we're going to make a model class, the RNN-GSN. Now the things we care about are just the RNN model and the GSN model. And these are 2 layers that exist already in the package. So we're going to initialize our RNN, which works over 3D tensors because you have batches of time steps, basically. So your first dimension in your 3D vector is going to be your batch, all the data laid out. The second dimension is going to be your time series, your sequence. So you're going to have batches of sequences in second dimension. And your third dimension is just the actual data itself. So you can think of it as batches of your sequences of your data. So our input size is still the MNIST images, 28 by 28. Our hidden size, we're just going to do 100 units for our recurrent neural network. Layers, we can make it a stacked recurrent network, but that'll make the training time a lot longer. Now, something we have to do is make the output size of the RNN the same as the hidden input size for our GSN, because we're taking the outputs of the RNN and creating something we can generate from with the GSN. So here, that's just the layers divided by 2 for the GSN, because that's specific to that model, but you only need half of the layers to represent it. And you can do the activation functions, how you initialize the weights, the uniform distribution with some nice fancy starting weights, stuff like that. Now for the GSN, we're just creating one GSN model that we're then going to actually use and loop for each of the times we're going in the sequence. So our GSN model, again, has the input size of 28 by 28, which is the images. It's going to have that hidden size that we talked about before, 500. And we can specify all the other things we would care about in the model here. In this case, it'll have 4 walkbacks, same as the denoising autoencoder. It'll actually generate a bunch of reconstructions. And then at each time step, the cost is going to be the sum of all the reconstruction errors. So the GSN inherently works on 2-dimensional data. So the input is a matrix, just like it was with the denoising autoencoder. But our recurrent networks are actually going to spit out a 3-dimensional tensor because it's working with a time series, right? So the GSN isn't used to time series. The RNN is all about time series. So what we're going to actually do is create a loop that applies the GSN to every step of the time series. And Theano, you do loops with something called a scan. You should look up the docs if you're interested in RNNs on scan for Theano. But basically, it applies a function, a given function, over the first dimension of an input. So in our case, the three-dimensional tensor, it'll apply that step function over every of the first dimension elements. So for every sequence, it'll extract out what that first sequence was and apply that to the step function. In our case, the outputs to the RNN is a three-dimensional sequence of the hidden values of what the GSN should be. So we're going to loop over all the hidden values that the RNN outputted, and then we're going to compare it to the original x using the GSN. So here, in our step function, at each individual time step, we have the output hiddens from the recurrent net. We have what the input, actual correct input was, x. We're going to create a new GSN with the same arguments that we had here. We can tie things using hooks, which is pretty neat. The inputs hook basically makes it use the same symbolic x input that we have for the entire RNN function here. The hiddens hook is what we're going to use to actually make it generate from the hiddens outputted from the RNN. So we need the hidden size and then the hiddens that was actually output. And then the parameters, make sure it shares the same weight parameter so we don't create new weights, so we don't, exploding our model parameter list. We're using the same weights for every GSN, which means the GSN acts as one model. You're learning the same set of weights across all of these. And then the outputs, this is just going to return the output reconstruction, and then it's going to return the training cost for the GSN. So in the scan function, we take that step, we're going to iterate over the outputs of the RNN, and we're going to pass in also the input x, and it's going to output a 3D tensor of all the outputted output reconstruction original images, as well as a 3D tensor of all the costs, one for each of those time steps. So all we need to do for the cost is to sum it all up. For the parameters, we get the GSN parameters and the RNN parameters together. And to make something trainable, we have to add just these functions, these helper functions. One is to get the inputs. This returns the inputs that we have for the entire model. Wants to return all the parameters. Wants to return the train cost. Wants to return the updates, which is actually used in scan. Scan puts out some of the updates for how to actually modify the variables over time. Again, scan is a very powerful thing, and if you're interested, you should read the documentation from Theano. And then the outputs that we got, which is the entire sequence of our reconstructions, the predicted reconstruction given all the previous ones. So that's how you create a model in OpenDeep if you want to create something very novel. This has weird dependencies, so we could do a scan. It's not just adding layer by layer. Now the same thing, we have our model, and we have this optimizer, this training algorithm, which is a separate entity. So you can sub out what you want to use to train. Before we were using stochastic gradient descent. Now we're going to use something called RMS prop, which is just a little bit of a fancier method. It depends less on your learning rate, and it lets you train things like recurrent nets a little bit easier than stochastic gradient descent would if you don't quite know what the right parameters are in the beginning. Another thing that's important for recurrent nets is something called gradient clipping. So recurrent nets, if you think of this three-dimensional input as your sequence over time, the hidden layers is actually unrolled over time a giant neural network, right? So the hiddens feed from previous hiddens into the next hiddens. If your sequence is 100 units long, you're essentially creating a neural network in the hidden space that's 100 layers wide. So something like that makes it very easy for the gradient information to either go to infinity or to go to zero, just based on the weights happening over and over again. So a lot of optimizers, what they do for recurrent nets is something called gradient clipping, which makes sure you don't go to infinity. It'll clip it at some number so that you always have a gradient, and you can always kind of make a step without losing that information. Just a tip for training recurrent nets. And this will take actually, Wi-Fi. Or maybe that crashed. It's still running. Demos. But basically, try to shut it down and restart it. But basically, it runs in the same manner. You just hit train, it compiles the functions for you, it'll use that optimizer, reduce the cost over time, and then in the end, with those reconstruction images, you can spit out what it thought the sequence should be. And in this case, it performs fairly well for a rather complex sequence. I mean, the dependency is 2 bits of information. You have if you're increasing or decreasing, and you have what the next number should be. So in summary, what is deep learning? Yeah? Yeah. So in this, well, the input's actually longer than this, but you can think of it as this entire matrix as one sequence. Don't think of it as the square. Think of it as all one line. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 through 0, 0 through 9, repeated for whatever the sequence length was that we defined. I think it was 50. Actually, it's less than this. Yeah, but you're giving the entire sequence, say 50 of these repeated. So the sequence does repeat itself many times in the input. But for each output, what that is it's determining for each number, it's predicting what that next one would be. So, and you can line them up like this just by shifting it over one. So this is basically what it should be on the left, or this is what it was given on the left, and on the right is what it thinks it should be. So in summary, deep learning all uses very basic building blocks. You have some transformation with a nonlinear function, and you stack those together. You compose nonlinear functions to get more representational power. And what that does is it lets you learn a hierarchical representation of your input, more abstract concepts from base inputs. How's it doing this? Again, it's with nonlinear functions. And it's learning useful features. You don't need to be able to hard code in, have your feature engineering person go and figure out what's actually important in the data. It'll figure out from having massive quantities of data what is actually useful. And that's the caveat with a lot of deep learning. The parameters are so large. I mean, these matrices can get really large, so your parameter space can be in the millions. And to actually learn something useful, you need a lot of input examples. But nowadays, with internet scale technology, that's not hard to get. You can just scrape a lot of things and get a lot of input examples. Again, the neural network, the MLP, is basically logistic regression. It just uses matrix multiplications, ending with a softmax to get your probabilities. And it works layer-wise. The denoising autoencoder is the unsupervised problem, where we're trying to reconstruct an original input from this hidden representation. Again, it uses the same functions that the MLP does, except in the end, it's not softmax classification. And the RNN-GSN combines 2 different types of networks into one. How does this work? It's because layers, I mean, they're all just matrix multiplications of different information from different models. And you can just connect them together with a matrix multiplication. And then you can train the entire network using the same training algorithm, because the gradient can be computed using the chain rule back through all of your parameters, and everything can get updated. And this is done automagically by Theano, and it is quite great. And the same principle can be applied for even larger networks, combining a lot of different types of models. You can have different types of inputs. Say you can have like a model that does your image inputs, a model that does speech inputs. You can combine all of those outputs into one layer. That one layer can then be a classification, and that could all be trained with the same algorithm. I wouldn't quite recommend that because it would be necessary to have like a lot of input data because the parameter space is really big, but you could do it theoretically. So the takeaways is that deep learning is the hierarchical representation. It has just basic building blocks. These basic building blocks are all composable. There's supervised and unsupervised learning, one where you have labels and one where you only have your input data. And complex networks are all just simply made by building up all of these basic units together. And that's it. If you have any questions, yeah? Mm-hmm.
What's the noise kind of?
Mm-hmm.
Is there like a work or, and also how would that respond to a different problem? Because this is an image, some kind of
Mm-hmm.
here.
Yeah, exactly. The main point of the noises stacked is regularization, so your individual like parameters aren't memorizing things. Here, you can do, what you basically do is noise is a hyperparameter that you play with. So you'd want to make it just noisy enough that it's not overfitting. And so you'd start with smaller amounts, and you can increase it if your model is overfitting. For different types of noise, right, this is binary, you want the noise function to be appropriate for your input or your hidden types. So we're using salt and pepper for binary, but you can easily add Gaussian noise. Just pull from a random, like 0 mean, 1 standard deviation distribution, add that on to your thing, or increase the standard deviation if your units you're expecting to have a larger variance. And you can use that as your noise function. And use the switch in the same way to turn it on during training, turn it off during testing. But yeah, exactly. Noise acts as a regularization, and you need to have the appropriate noise function for what input or hidden units you're adding the noise to. Yes. So yeah, in the case of denoising autoencoders, you need to have that noise, the type of noise it's adding, to be appropriate for the type of input data you have. So for the images that are binary, we're doing the salt and pepper. As far as using noise in the hidden layers, like dropout for the MLP, you can actually just use the dropout, which just sets a masking of 0, because that essentially makes each individual unit in the hidden layer unable to access all the information for each example. So what you're doing is you're preventing individual units from having an effect on the output, because you're setting those units to 0. So dropout noise actually is applied as regularization regardless of the type of data that you're using, but that's generally only on hidden or intermediate layers. For input noise, for denoising autoencoders and such, you just have to know about the input domain and use the appropriate noise function.
Questions? Take advantage of his knowledge. It's encyclopedic, like 10 years of reading papers. That'll save some time.
Thank you for picking such clear examples, really helpful, basic examples. And it made me curious about your own personal research about what kinds of applications you're trying to use this for, or what kinds of things do you think are the edge of trying to figure out answers to questions that might not be such as good teaching opportunities, but are of personal interest?
Yeah, what I'm really interested in is unsupervised learning of like sequential data. So, I mean, one thing I've played around with, of course, is some stock data, as pretty much all machine learning people have. And using recurrent networks is a very good way to model time series data. Specifically, their recurrent network actually can be thought of as a framework in itself rather than a basic building block. Recurrent networks have like an input to a hidden function that can be deep. You can make your, just like for the RNN-GSN, that had a hidden to output function having depth. The GSN is the hidden to output function reconstructing. You can have your input to hidden function also be having depth, and then you can have your hiddens to hiddens function be very deep. And what that lets you do is create a recurrent network that can model very complex input data. So what I'm personally interested in is taking a lot of like different types of data sources, like images, performing like character extraction from these images, or like scan documents, using like a visual attention mechanism, or like combining those with other inputs you'd find from scraping the web to create like a larger classifier. Having like these modular components is what I work a lot with.
How much control do you have over the various attributes of the model? For example, suppose I didn't want to add noise, but I wanted to like rotate the image or scale the image, do different kinds of things like that, and because that can give advantages too.
Yeah, you can do any of that. Again, with Theano, it's basically just like writing the math. So for any scale or rotation of images, that's another matrix multiplication. the affine transform of using a matrix that will then rotate 90 degrees is a certain matrix type. So when you're writing these models, your input is that symbolic X matrix. You can then, before you perform any computations on that input, you can rotate it, scale it, modify it kind of in real time while it's running. And you can actually also set a switch so that that only happens during training and not during testing, or you can do all these sorts of things. But yeah, if you want to take any equation that you would write in math, you can implement it in Theano in the same exact way and use that output to form like a computation chain. Yeah, I mean, there's plan in OpenDeep. It's still in alpha to actually add those utility functions that let you augment your data in real time as you're streaming them in. So you can scale images, you can rotate them, all sorts of normalization techniques. But yeah, it all works because you can just stack those on top of your input data variable, and right before you have it fed into your matrix multiplication to form the hidden layers. So you can do any sort of transformation that you'd want with the data in a very easy manner. And that's generally useful, especially for augmenting your data, right? So most people don't have millions of examples of things. And what's commonly used in things like speech recognition is to actually augment your data of speech samples by putting background noise around them. Like I think Microsoft has put like cafe chatter in the background of samples and like switch out what different background noise is happening. And you still have your input data, but you have like a lot more examples with different versions of noise. Yeah. I don't think so, not that I know of. Yeah, it's numeric. It can only, I mean, it has built-in base operators that runs on the GPU. And they have hard-coded in like what the derivatives for each of those individual operators are, so then you can use the chain rule on it. But I think it's using a numeric approximation. It's not, it's not doing an analytical. I haven't dove too deeply into the base mechanics of the operations, staying more high level in that. But I definitely plan to try to make things faster.
So in all of your examples, you use stochastic gradient descent to train, but deep networks are a very non-convex loss functions. So I'm just wondering if in your work or in the literature you read, is there an advantage of using more complex like second order methods or other methods for optimization?
Yeah, most of the time stochastic gradient descent with the right parameters performs as well as you can find with anything else. I've only ever played around with second order methods of Hessian free stuff for recurrent nets, work from Ilya Sutskever. And it's just those types of methods take so long during computation that it's almost unviable to do right now. What works well in practice is using these adaptive learning rate methods like AdaGrad, AdaDelta. They are much more forgiving of your input hyperparameter values and let you find a pretty good solution. What I found is more important using those is your initialization strategy for your weights. If you're going to, like what standard deviation you're going to pull from to randomly sample in the beginning, or if you're going to use a uniform sample, like what interval you're going to do. And there's a lot of literature, and it's a highly active research area to pick the correct values for those. But yeah, second order methods and other things like that, just right now, they take too long to run in real time.
So this implementation assumes one CUDA core, right? So when would you add multi-threading on the GPU for this?
Multiple GPU is in the development version of Theano right now. I haven't personally worked with any of their multi-GPU stuff. But yeah, it'll be useful for model parallelization, which speeds things up a lot. Right now, you can do the two things to speed up your model with parallel stuff. You can do data parallelization or model parallelization. Data parallelization, you actually don't need to add more like Theano cores. You can do something called like parameter averaging. So you take multiple copies of your model on different machines. They learn parameters. You take those parameters learned, you average them in some base master distributed network, and then you can put back out what that average was as the new parameter updates. And that lets you parallelize your data processing. Model processing needs to have that multi-GPU support, which is in development, but I haven't played around with it.
Quick question on you mentioned that you like time series problems as an application for these neural networks and recurrent neural networks in particular. Can you talk about a couple of examples? I'm working with a time series problem, and I'd like to see, I guess, a little bit of an explanation of how you apply it.
Yeah.
Thank you.
So what was recently put up was a tutorial actually by Andre Karpathy on his GitHub, which is creating a character-level language model using recurrent networks. And what that does is it takes in a sequence, which is just a large stream of characters of any text. You know nothing about the language. You know nothing about like words. You only know the characters, which is a small space. Your vocab size, maybe you'll have 60 characters that you can represent. The recurrent network, what it does is it learns, given all previous characters, what the next character should be in that sequence. And you can use this to generate text from this language model. And that's really interesting because if you have a language model that's learned from a character basis, it's like language agnostic, it's symbol agnostic, and you can start to classify like words or other things that you would care about from these characters by adding like an output classification layer on top of what it's being learned. So things like that are really useful.
Any other questions?
Can you talk a little bit more about OpenDeep? What's the scope of the project? Who's behind it?
Yeah.
Where are you going?
So it's basically just been starting. It's me and one other contributor right now. The internet. That's unfortunate. But yeah, it's on GitHub. It's in alpha right now. So it'll be beta ready, I think, in the next month. What's really missing is a really good recurrent framework. I have your normal recurrent networks up. I want to make the basic framework where you can add arbitrary depth to those hidden functions, to the input function, to the output functions. You can reverse it. You can do all sorts of things, making that generalized. But other than that, I mean, it has your basic dense layers. It has all the classifications, all the configurations you'd want. It has convolutions. It does some pooling. It has a bunch of data sets. It has the MNIST data set. It has the CIFAR-10 image data set. It lets you input text characters. It lets you wrap data that you already have in memory. Say if you have a NumPy matrix, it lets you wrap that and use it as a data set. But its whole philosophy is having something that's very modular and highly configurable to whatever your actual requirements are. Because I felt that when I've been making it, too many packages out there are too black box. You can't configure it to spit out the hidden values for a GSN given your recurrent network, or hidden values for any generative model, and have that run through. You can't really do these complex interactions of sharing parameters between different models. So these modular ways of composing, neural networks, I think, are very important moving forward, especially because most machine learning algorithms, I think, in the future are going to have an aspect of deep learning to it. It might not be the primary aspect, but with things like neural Turing machines, like deep reinforcement learning, stuff that combines different machine learning algorithms with a deep learning kind of base for representing the input data is very important. So that's the main driving philosophy, making something very modular, highly configurable to whatever future-proof way of composing deep networks should be.
Any other questions? Oh.
How does OpenDeep compare to others like Blocks, Lasagna, Keras, etc.?
Yeah. So I like all those packages. I actually borrow some code implementation from pretty much all of them for different functions. Keras is great. I met up with Francois recently, and it's also very modular. It has a good mindset, but it's trying to be more minimalistic and not as highly configurable. Which, I mean, it has its plus sides, right? So that's more of a torch interface where you can quickly throw together a prototype model and let that run. For blocks, that's the successor to PyLearn 2. It's still, in my mind, a little bit too complicated to use. It's hard to get into, hard to learn, not clear enough in my mind. And it does have some powerful people behind it, of course, in the Lisa lab, same people who actually made Theano, working on blocks, as well as they had PyLearn 2, which was the previous package. And Lasagna is great. I mostly have the convolutions from it. Sander's really good for those. But again, I think Lasagna isn't the quite abstraction level that's correct for like composing things in arbitrary manners. So all these, like every package has to make some base assumptions on how to construct a deep network. Like what are building blocks? What are the hyperparameters? What do you consider a layer? And yeah, just as, I mean, I've been developing this pretty much in parallel with all of those guys. And it's just a different level of abstraction and a different philosophy for how to compose things together.
What do you think of Bayesian optimization techniques for neural nets?
Yeah, I haven't used any, but from what I've heard, they're all like very useful. They just increase your compute resources a lot. Mostly right now, it's the Spearmint package that's highly popular for doing those. I know in most research communities, it's pretty much still just a grid search for hyperparameters that's being done. You have your grad students go out and try different configurations. So it's still a very active research field, but I mean, I've heard good things about Spearmint and using. So Bayesian hyperparameter optimization is a way to more intelligently pick what hyperparameters to try next based on like previous results. And yeah, there's a popular package on GitHub called Spearmint.
Markus, do you have these notebooks somewhere where we can access it?
They're on the GitHub.
Oh, fantastic. Any other questions? Huh?
So I'm kind of amateur in this field, and I've been playing around with deep learning and recurrent neural networks. I have no doubt that they're very powerful, but oftentimes I find myself with just a matrix of weights, and I was wondering if there's any way to guide the intuition of what's going on behind the scenes.
Yeah, definitely. There's a lot of research being done into like the visualization of what those weights are learning. In the case of that single layer, as we saw before, you can actually just make an image of the first layer weights, and that shows you kind of the activation map. There's some visualization tools. This came out of NYU. It's called TSNE, which lets you kind of see what neurons in higher level areas are activating based on different properties of your input. So it'll like try different kind of configurations of your input, kind of see what's being activated in higher layers, and kind of make an image of that. So you can see those filter maps. Things like in the beginning here, stuff like this can be outputted, where you can kind of see what textures each layer is learning based on the inputs. And that's a highly active research field, and it's definitely useful during debugging to actually output stuff like this, these visualizations, every certain number of epochs, so you can kind of get a sense as, okay, is my network actually learning things? That was kind of one of the reasons why we were outputting the checking points for the denoising autoencoder every 10 epochs. We could see kind of the reconstruction. Okay, yeah, it looks like it's trying to denoise things. It's getting better over time. Same thing with the weights. You can look, see, okay, are these filters being learned? Do they kind of make sense? Do things start to look like objects in higher layers? Do I see like edges and different like colors being detected? Stuff like that is very useful and definitely necessary in the debugging phase.
All right. Thank you so much, Markus. This was wonderful.